Good afternoon. Welcome to today's Wednesday afternoon lecture. I'm Belinda Cito with the National Institute of Biomedical Imaging and Bioengineering. I have the pleasure of introducing this afternoon's lecture speaker, Dr. Rebecca Richards-Cordum, who is the Stanley C. Moore Professor in Bioengineering from Rice University. She also directs the Institute of Global Health at Rice. Prior to joining Rice University, she held various academic positions at the University of Texas in Austin, where she had really a meteoric rise from assistant professor to full professor and an endowed chair for bioengineering there. She got her PhD and her master's degree at MIT, and after graduation there, after her degree there, she received numerous honors, including the National Science Foundation Presidential Early Scientist Award, the Presidential Faculty Award. She was named the Howard Hughes Medical Institute Professor twice in 2002 and 2006. She was elected to the National Academy of Engineering last year, but most important of all, she served on our Institute's Advisory Council, our inaugural council, for which we are completely indebted to her dedication and her service there. Her work has, through the years, focused on optical imaging system for early detection of precancerous detection for oral cancer, cervical cancer, and esophageal cancer. You will actually be treated to a demo this afternoon. She personally embodied the interdisciplinary theme and focus of my institute. So before I turn the podium to Dr. Richards-Cordum, I want to thank Chris Kelly, and member of the NIH Working Group on Women and Engineering. They have done the yeoman's job, especially Chris, in submitting the nomination and organizing the events for Dr. Richards-Cordum today. So without taking further time, I will bring Richards-Cordum to the podium. Her title of her talk is From Cell Phone to Cell Biology, High-Tech, Low-Cost Solutions for Global Health. So we're in for a treat. Thank you.
Thank you. Thank you so much for the invitation to be here today. It's really a pleasure to be able to join you. I want to begin with a financial conflict of interest disclosure, which is that I hold equity in Remicalm, a company that is commercializing cancer screening technologies. With that out of the way, I want to begin with a picture that has a lot of personal meaning for me, and I'd like to just tell you a little bit about how I came to take this picture and why it is so important to me. As Belinda said, I'm a bioengineer, and I'm interested in vivo microscopy and molecular imaging for cancer prevention, and I've had a strong focus on women's health issues throughout my career. And I've also been very interested in engaging undergraduates in research and drawing more women to the fields of science and engineering. But until about 4 years ago, when I thought about drawing more women to engineering, I have to say, these were not the little girls I was thinking about. And when I thought about women's health, it wasn't their mothers that I was thinking about. And I got a grant from Howard Hughes Medical Institute, and part of that grant was to develop a course in bioengineering and world health. And I learned a tremendous amount in developing that course, and it totally changed not only my teaching, but it changed the way I did research, and it changed fundamentally the way that I thought about designing technology and designing for an extremely constrained environment. And so I'd like to share a little bit of that story with you today, because I think taking that approach and thinking more globally can help us address some of the challenges with the escalation of healthcare costs and disparities in the availability of healthcare technology. And I think it can also help us improve the diversity of our scientific and our healthcare workforce. Now, I took this picture in Malawi outside a hospital called St. Gabriel's Hospital, which is in a rural part of the country. And it's a really wonderfully run hospital run by a Malawian order of nuns. And for me, one of the things that this picture symbolizes is the nearly 9 million children under the age of 5 who die every year. 98% of those deaths occur in developing countries. And I think one of the most tragic things about that statistic is we know that 2/3 of those deaths could be prevented. And they could be prevented with technologies that exist today and are affordable in developing countries. And so in many ways, just like I didn't think about little girls like this, the world has forgotten about little girls like this, and technologies that exist just don't reach them. So I'd like to tell you about some of the programs that we've put in place to try and design technologies that can improve healthcare in these settings and think about what the impact of those could be truly in a global sense. Now, if you follow these little girls around the corner, you come to this building. And at St. Gabriel's Hospital, they don't provide meals to patients, and so family members have to come and prepare meals for their relatives who are staying at the hospital. And as you come further around the corner, you begin to get the sense that this might be a health risk. And as you walk in the door, you can see the extreme indoor air pollution that mostly mothers and their small children are exposed to as they're preparing the meals for their family members who are staying at the hospital. This is taken inside the pediatrics ward at St. Gabriel's, and you can see the mosquito nets hanging. This photo was taken during the dry season, but during rainy season, typically each bed will have 3 or 4 children occupying that same bed, and you can't be admitted without an adult to provide your minute-to-minute, day-to-day care, and so you see a lot of moms sleeping on the floor next to their child who's in the hospital. This picture was taken in Lilongwe, the capital city, at Kamuzu Central Hospital. And again, you can see where pediatric patients get their bath. It's outside in the patio adjacent to the hospital. And this is the nursing station in the pediatrics ward. And at Kamuzu Central, on average, for every 70 children, there is 1 nurse that is available to help provide their care. So it's an extremely resource-constrained environment. And so as we think about what are the technology needs for this environment, we have to deal obviously with a lack of predictable electrical power, perhaps a lack of availability of clean water, lack of spare parts, and knowledge to repair equipment. And this picture for me really symbolizes that. It was taken at a government hospital in Swaziland, and you see an elevator, and in front of that elevator is an X-ray machine, and actually the elevator is broken, as is the X-ray machine. And the X-ray machine is being used to block the entrance to the elevator. So you could argue that it's an appropriate use of technology, but it really points out the extreme limitations that we have in trying to design technologies for this type of environment. And so in our lab, what we're thinking about, and in my colleagues' labs at Rice, we're thinking about how we can use advances in microfabrication technology and in consumer electronics, how we can leverage the hundreds of millions of dollars of investment that has been made in this country to design healthcare technologies that have minimal power needs and can be automated and can function at the point of care. And if we think about the potential impact of improved point-of-care diagnostics, there was a study published in 2006 that looked at the impact that better diagnostics for TB could have or for malaria. And you can see that the potential to save lives is enormous if we had better diagnostics. And the potential to reduce unnecessary treatments and prolong the activity of anti-malarial agents is really extraordinary. And if we think about how that's done today, light microscopy is one of the most important tools in detection of malaria and detection of TB, and it's basically a 400-year-old technology. If we use bright field microscopy, we can identify bacilli or parasites in sputum smears or in blood smears. But we know that using fluorescence microscopy, we can simplify the staining procedure, we can increase the sensitivity, and we can reduce the examination time. The challenge is that placing a fluorescence microscope in an environment where there's limited power is a difficult thing, and they tend to be very expensive. Zeiss Microscope Company collaborated with FIND, the Foundation for Innovative and New Diagnostics, to develop an LED-based fluorescence microscope. And this is about a $2,000 microscope, and it gets beautiful quality images, but it still requires power, and the cost is still out of reach of many health centers in the developing world. So we'd like to think about how we can make microscopy more cost-effective and how we can expand the range of microscopy to improve its sensitivity and its specificity. So I want to tell you about one of the students in our undergraduate design project who designed a fluorescence microscope that can be manufactured for $220 that uses battery-powered LED-based flashlights as the light source. And I'd like to tell you also about the use of microfabrication technologies, which have been developed in collaboration with Tomas Tkaczyk at Rice and Mike Discore at the University of Arizona to develop even smaller, even lower power, and even less expensive microscopes that can image in bright field and fluorescence mode. So we can go from the $40,000 to the $2,000 down to $200 and potentially even down to the $10 order of magnitude for price. So our student design microscope is called the Global Focus Microscope, and it uses standard microscope objectives but battery-powered flashlights as the light source. And here you can see it will do 100x oil immersion. These are 40x images. This is malaria, and this is a TB smear shown in bright field and shown here in fluorescence. And this fluorescence picture was actually acquired with an iPhone. And so using inexpensive cell phone-based cameras, you're able to capture and digitize images with diffraction-limited spatial performance. You can also use cell phones in conjunction with other standard microscope objectives. This is work from Dan Fletcher's group, where he was looking both again at malaria and at TB and fluorescence mode. And so leveraging these advances in consumer electronics allows us to dramatically reduce the cost and the size and the power requirements of these technologies. But we can go further if we use microfabrication tools. And shown around this quarter is a whole series of microscope objectives. So this is a $2,000 standard microscope objective from Olympus, and a whole series of diffraction-limited microscope objectives that can be mass-produced in inexpensive ways using microfabrication tools. And I'll just show you some of the designs. This is the design of this objective right here. And here we're moving to this objective right here at 5 o'clock, and you can see we're down to 3 optical elements that are part of this objective. And these lenses can be assembled inside a piece of metal hypodermic tubing using special springs that are designed to go inside the tubing and compensate for the variations in the diameter of the tubing. So they cause the lenses to self-center so that all you have to do is stack together the components and the device self-aligns to give you diffraction-limited performance. And to show you that, here are 2 slides. This slide was they're the same slide. This image was acquired with this objective. This image was acquired with this objective. And so we can yield very high-quality images using these advances in fabrication technology. We can go beyond bright field and fluorescence microscopy, though. If we look at the ability of light scattering microscopy to highlight the presence of pathogens, we open up the opportunity to detect the malaria parasite without the need for stain. And so here you see a white blood cell and you see evidence of the malaria parasite. Here we're looking at it in bright field, but this is looking at it in dark field. And you can see the light scattering associated with the parasite, the hemozoan byproduct in the white blood cell. And here you can see the light scattering associated with the ring form in the red blood cell. Now in my lab, we do a lot of work with confocal microscopy for in vivo imaging. And if we can identify the parasite based on endogenous optical properties, we can easily image red cells and white cells in the capillaries in vivo. And so I'm going to play a video for you. And this is a video, we're imaging the lip, and we've started at the surface of the lip, and we're going deeper. And right here, I don't know if I have a laser pointer, right here we hit the capillaries. And for some reason the video stopped. There we go. So the nuclei are here, and here you can see red blood cells. There was a white blood cell that went through this capillary. So we have the potential to have a reagent-free diagnostic to look at malaria without the need for doing a finger stick. And we're just at the very beginning stages of developing this and evaluating its potential for in vivo use. Now, using advances in nanotechnology, we can also look at point-of-care diagnostics to look at nucleic acid targets. And so if we take metallic nanoparticles, we know they're optically active, they'll scatter and absorb light, and we can functionalize the surface of those metallic nanoparticles with oligonucleotides that are complementary to a sequence that we want to probe for that's associated with our pathogen. And if we choose two sequences that are adjacent to one another on our target, if our target is present, it will induce the aggregation of those nanoparticles, and that will change the color of the light scattering. And so we can go from a reddish color to a bluish color in solution. Or if we spot it on a glass slide and look at the light scattering, we go from a greenish color in the absence of target to an orange-reddish color in the presence of target. And we're sensitive to very, very small amounts of target. We can detect as few as 10 attomoles of target using this technique. We're looking at this to detect Cryptosporidium in stool samples, where we're targeting the HSP70 mRNA, and we can actually use the organism itself to amplify the HSP70 mRNA simply by heat shocking the organism, and then equilibrating it with the targeted nanoparticles and looking at this increase in scattering in the red region of the spectrum. And we're also looking at the same test to look at Plasmodium falciparum. Now, my colleague John McDevitt is working to integrate these chemical probing techniques with microfluidic devices for point-of-care tools to help better manage HIV-positive patients. And what John has done is to develop a portable device to look at CD4 levels to help better manage HIV-positive patients. And in this device, there is a membrane which has holes that are sized to allow red blood cells to flow through, but to trap white blood cells on the surface. And then you can do immunofluorescence staining of those to look for CD4 positive lymphocytes, and use basically a microscope, a fluorescence microscope, to capture images of those. And when he correlates that device with a flow cytometer, you can see that the correlation is excellent. And here is the reader and the microfluidic card going into the reader. And you can reduce the cost of a typically $50,000 flow cytometer to a couple $1,000 and truly do a test at the point of care. Now, I'd also like to think about how we can use these technologies to improve cancer screening globally. And normally when you think about global health needs, cancer is not what is at the top of your list. But if you look at the number of global deaths due to cancer, it exceeds that due to TB, HIV, and malaria combined. And if we look at the projection for the increase in the number of new cancer cases globally, you can see that the vast majority of the increase between now and 2020 will occur in developing countries, which have the least resources to deal with patients who have invasive cancers. And if we look just at the cost effectiveness of screening for cancer in developing countries, I'd like to show you some of Sue Goldie's data from Harvard. She looked at the cost effectiveness of screening for cervical cancer. And what's shown on the y-axis is the percent that you can reduce a woman's risk of developing cervical cancer during her life as a function of the amount that you spend screening during her lifetime. And so here are several different strategies, and you can see we ultimately reach the point of diminishing returns if we're screening with the pap smear and HPV DNA testing every year. And so if we look at the slope of this line, we can ask the question, if I invest an additional $50,000 in cervical cancer screening, how much additional life will I buy? And if I ask that question in the United States, the answer is 15 weeks. And we judge that to be a good use of resources. But if I ask that question in South Africa, my $50,000 will buy 1,000 years of life. So it's a huge discrepancy in the good that we can achieve with this investment of resources. So why do we not have more widespread cervical cancer screening programs? It's a leading cause of cancer death for women in developing countries. And in particular, in countries that have a high HIV prevalence, women who are immunosuppressed are at much higher risk of developing cervical cancer. This picture was taken at a rural health center in Swaziland, and you can see some health posters up here on the back of the wall. And one of the posters says, "Attention women attending an HIV/ARV clinic, have you had a pap smear?" And it goes on to explain the importance of cervical cancer screening. So I asked the nurse at the clinic how many pap smears they do, and the answer was none, because they don't have the infrastructure or the supplies or anyone to read the pap smear. Because to do a pap smear, you need to be able to stain the smear, you need a cytotechnologist to read the smear, and then you need to be able to follow that up with colposcopy and biopsy. That's the standard of care here. So our lab had a big interest in doing confocal microscopy to improve cervical cancer screening at the point of care. And you began to see research-grade systems to do this developed in the 1990s, and they looked something like this. They were on a big cart. You had to design microscope objectives to allow you to do in vivo imaging. But when you could do it, you got beautiful histologic quality images. And so these are confocal images of normal cervix and confocal images of precancerous cervix. And you can see the increase in the nuclear size and the nuclear crowding associated with precancer. And now in the 2000s, we're beginning to see commercial systems to do confocal imaging. So we have very complicated and very expensive confocal microscopes that are limited primarily to tertiary care centers. This is the Pentax confocal, the Cellvizio confocal, the Lucid confocal. They're all $100,000 plus instruments. They give beautiful images, but they are not going to help those women at that clinic in Swaziland. So we began to think about how could we get the same information in a lower cost portable package. And I'm going to hopefully demonstrate for you the approach that we've taken. So we're using cheap LEDs, a $10 LED as the light source, and we've coupled that to a fiber optic fluorescence microscope. You can see the fiber optic device there. We can achieve about 4 micron spatial resolution. The device runs on a laptop battery, and it fits inside a portable briefcase. And we can use it to image nuclei. So I'm going to try an experiment here to demonstrate the microscope for you. We use a fluorescent dye called proflavin, which we label nuclei with. And so I'm just going to put a drop of proflavin on here, and we'll see if this works. You can see the blue light coming out of the tip of the fiber bundle. And the device is a contact imaging device. There we go. So what you see are nuclei, the little white dots that you see, and you can see some cells have stuck to the end of the probe. There. So we're able in real time to image nuclei and to image the nuclear enlargement that is associated with precancer. And we're carrying out a clinical trial of that device now at Methodist Hospital in Houston to look at whether or not it can help us recognize precancerous lesions. And these are some images from the trial. This is normal cervix and squamous metaplasia, a normal finding. And these are 3 grades of precancerous lesions, CIN1, CIN2, and CIN3. And you can appreciate the increase in nuclear crowding. And we can actually process those images to quantify the nuclear to cytoplasmic ratio. And what we have found is that a threshold of about 0.08 does a good job of separating high-grade precancer from low-grade precancer and normal tissue. But we can further leverage advances in consumer electronics. So we can take a digital 35mm SLR camera that we bought at Target, and we can use that actually as the image sensor in our microscope. So here's the bundle coming out of the front of the microscope, all of the optics in the microscope, and then you can visualize the image on the LCD screen of the camera. And this is an image of the cervix that was obtained with this 35mm based scope. I think having a low-cost device is important not just in Swaziland, but it's also important in the United States. We know that cancer screening rates are twice as high for people who have health insurance as those who don't. And we know that cancer patients who are uninsured or who have Medicaid are more likely to be diagnosed at a later stage and have significantly lower survival rates. So I think low-cost technologies like this can make a big impact. But at the same time, we have to think about having high-performance techniques. As we look at oral cancer screening in this country, there have been a number of advances to improve oral screening that are based on cytology or based on visual changes in surface mucosa. So oral CDX, advertised in the New York Times, Sunday Magazine all the time. The Veloscope is a commercial device to image autofluorescence that has been on the market for a couple of years now. And there is concern that these new tests may not add sufficient value. This is from an article in the New York Times from February, and they say these new tests have set off a debate over cost and effectiveness. Experts are divided on whether they will reduce mortality from oral cancer or simply lead to a wave of expensive and unnecessary biopsies. And so I think some of these technologies that we started out designing from the perspective of meeting global health needs, where low cost and high performance are imperative, can help us address this as well. We've been working in our lab to develop imaging tools also for oral cancer screening, another important global cancer. And what we found is that the loss of autofluorescence gives us very sensitive and very specific identification of oral premalignancy. You can see here the results from an independent validation set with sensitivity of 94% and specificity of 87%. And if we process those images to identify areas of precancer, and then we correlate that with the underlying histology, going from A to B here, for example, we see an area of carcinoma in situ. So we get good correlation with the underlying histopathology. But as these technologies are being translated into the community setting, what people are finding is that they're helpful in identifying occult disease. This is an area that was not suspicious by white light, showed loss of fluorescence, and in fact corresponded to a submucosal cancer. And here's one type of benign lesion, did not show loss of fluorescence, and was just hyperplasia. So everything looks good based on that. But what people are finding as they go to a community low prevalence setting is that lesions like this show loss of fluorescence, and they correspond only to inflammation. And so a tool where inflammation results in false positives will drive cost of biopsy and subsequent follow-up. And that's where I think the combination of wide field and high resolution imaging can really play a role. With the wide field imaging, we can identify suspicious areas with high sensitivity. And then we can come in with in vivo microscopy and tell normal apart from precancer, apart from invasive cancer. And in fact, when we look at benign inflammation or inflammation and cancer, with the high-resolution imaging, we're able to segment the nuclei and look at the changes in nuclear to cytoplasmic ratio to help us improve that diagnostic specificity, which is so important. And so we're now working to combine the wide field imaging and the high-resolution imaging in a single device. And here you see the microscope, the fiber optic microscope, the wide field image, and the microscope image all together operating in tandem. Now, in the time I have left, I'd like to think about other ways that we can meet these needs. And I'd like to think about education as another type of technology that can be very important in improving global health. This is a poster that I saw at the Ministry of Education in Malawi. I just love this poster. It says, "Education is the social vaccine for HIV. Boys and girls, complete your education." What we have done at Rice over the last 3 years is to develop a new program in global health technologies. It's an undergraduate minor, and it's open to students who are majoring in any field. And what we do in this program is we teach students the process of engineering design as a way of helping guide them through structured problem solving. So they begin in the freshman year with a problem-oriented design course, and they continue through to a capstone senior design. And the problems that we choose come from practitioners who are delivering healthcare in the developing world. And the Baylor International Pediatric AIDS Initiative in particular has been a very important partner for us. And this program is funded through an undergraduate science education grant from the Howard Hughes Medical Institute. And I want to show you some of the results of our student design technologies. We worked with a medical brigade team that traveled to rural Honduras to an area with no electricity and no water. They went every 6 months, took teams of physicians and students to provide health care, and it was very difficult for them to provide the diagnostic services that they needed to determine which patients needed to be referred and to appropriately treat them. They wanted a lab in a backpack, and so our students designed a lab in a backpack. It runs on a laptop battery, and that laptop battery can be recharged from a solar panel. Everything that requires power plugs into a central control unit. There is an otoscope, an ophthalmoscope, a mini centrifuge to spin hematocrits, and a 100x oil immersion microscope. There is a glucometer, a pulse oximeter, urinalysis test strips, and other rapid diagnostics. We initially sent 8 of these packs out into the field, and those 8 packs have now been used to care for more than 4,000 patients in collaboration with a variety of healthcare providers. And 2 of the students who designed that, Jenna Mueller and Jeannie Ling, were recognized at the last Clinton Global Initiative University meeting. They traveled to the developing world during the summer, the students do, to take their technologies and implement them in collaboration with partners working in the field. And here is Jenna and another student, Christine, delivering the backpack to a Partners in Health clinic in a rural area of Lesotho. This clinic was a 6-hour hike from the nearest road, and they left it with Dr. Leroy, who said to them, "Now we'll have a little hospital when we travel out to the villages." The Ministry of Health in Ecuador has requested 24 of those packs, and you see here our pyramid of backpacks, which will be shipping out to Ecuador in January for countrywide coverage of the diagnostic lab in a backpack. That spurred the development of several other types of packs. A pack for obstetric and gynecologic care. You can see here it has a portable set of stirrups that are made of plywood that can be used to turn any table or bed into a table for a gynecologic exam. A blood rocker so that you can do syphilis testing at the point of care, and all of the tools that you would need to do prenatal exams or to do cervical cancer screening. An eye care pack recently followed, and here you see the eye care pack on an ox-driven cart. And this was used by a foundation called the Shanta Foundation to deliver eye care in Myanmar. And this is Fred, one of the physicians that we worked with there, and he wrote back an email I want to read to you that I was able to send on then to the students who developed the eye care pack. He said, every patient we saw in these remote villages in Myanmar was indirectly touched by the hands and minds of all the students who developed this concept and final product. I hope you share that thought with all of them and that they have some realization of the gift they have provided to people in another world whom they will never meet, but who nevertheless will have their lives changed through the preservation or restoration of sight because of them. It was a really good day when we got to forward this email on to the students who developed this backpack and for them to see the impact that their work as undergraduates was having globally. We've worked with a wonderful pediatrician named Liz Molyneux in Malawi, and in her pediatrics ward, she has a number of incubators which have broken and they're not able to be used. And so she worked with another engineer actually to design a low-cost incubator that used 4 light bulbs to warm the air inside the incubator. And our students were able to work with them to improve the thermal design of this to significantly reduce the cost of the incubator. But what she also wanted was a way to treat babies who suffered from neonatal jaundice. They had only one set of phototherapy lights in her hospital, and they weren't able to provide care for all the babies who suffered from jaundice. And so our students developed a set of phototherapy lights that can be manufactured for about $30. They use the same blue LEDs that I have in this microscope here. They're about 11 cents each, and they're rated for 10,000 hours. And we've now been able to deliver 10 sets of those phototherapy lights to Dr. Molyneux in Malawi. And you can see here the first generation that was developed. She gave us feedback, and a student worked as part of an independent study to incorporate that feedback. And when she went to the hospital to deliver the improved lights, what she found was that the first set of lights was actually being used that day to treat 2 babies who were suffering from jaundice. She talked to Dr. Molyneux about the need for another project, and that was to control the flow rate and the volume of IV fluid delivered to babies. And in treating babies with IV therapy, typically in the developing world, you often only have 1-liter bags of saline available. And when the ratio of patients to nurses is 70-1, the risk of overhydration is quite serious. And so physicians are reluctant often to start babies on IV therapy because of the risk of overhydration. So the student now has been working to design a battery-powered drip monitor that will count the drips in the drip chamber of the IV and then incorporate a motor to control the flow. And we think that we can build these for on the order of $50, and again, they run on a cell phone battery. And you and the student who designed it will be taking it out into the field to evaluate it this summer. It's not only senior or advanced students who can contribute to the design, though. If we think about a very simple problem, and that is the accurate delivery of liquid medication. Often an oral dosing syringe is used to deliver liquid medications. And for prevention of maternal to child transmission of HIV, we use 2 liquid medications, nevirapine and AZT. And the dose for AZT is the same for all babies. It's 1.2 milliliters every 12 hours. And so pregnant moms who are HIV positive are given a pack at 20 weeks gestation and given instruction, but the instructions probably aren't often repeated again. And so the physicians that we worked with wanted a syringe that could be modified so that it could only be pulled up to deliver 1.2 cc's of fluid. And so we had a team actually of 2 sociology students and 1 freshman. They came up with an ingenious idea, and that is to take a dosing syringe and make a plastic clip that you could just clip in to the dosing syringe. And so they came up with one design that they drew, and they used our 3D plastics printer to print the first prototype, and that wasn't strong enough. So they put a ridge on the outer edge, and then it became too difficult to pull the plunger back with that. And so they redesigned it. They had a rounded edge right here. And the result now is a simple part we can make on our plastics printer for $0.25 and can be injection molded for less than a penny and can easily take a dosing syringe and by modifying the length of this piece to deliver any desired dose that you're interested in. This semester, we've had students working to develop hematocrit, ways to measure hematocrit. This is a centrifuge, which I just love. It's based on a salad spinner and combs. And I think any day you can take kitchenware and beauty products and turn it into global health devices. It's a good project. So here you can see Sally, as she's known, the salad spinner. And you can actually, in 10 minutes, spin a hematocrit. It reads a little bit high right now, so they're working on adjusting the gear ratio so that they can get an accurate reading with this. Another approach, though, is to use the WHO color scale for reading hemoglobin levels, and then to control the lighting. These are tiny little battery-powered fluorescent lights. To take your filter paper with a drop of blood on it, put it next to your color scale, use your digital camera on your cell phone to take a picture, and then you can match the color saturation and the hue to read off the hemoglobin level. And here's the hemoglobin level from the automated cell phone-based system compared to that of the HemaQ. And actually quite nice correlation with a very simple approach. So through this program, we've sent students and technologies all across the globe. And the impact on the students is, in many cases, really transformative. This is Neha Kamath. Neha was a senior when she traveled to Lesotho to implement a course that she developed in micro-entrepreneurship and health. And I wanted to read just a short quote from Neha's blog to give you some idea of the impact that this experience has on the students who are able to participate. The day that Neha wrote this blog, she took a group of high school girls that were in her course out to have a talk outside. And she said, "We sat in a circle and I told them that having their own money, regardless of how much they love their partner or how safe they feel at the moment, is essential. We talked about how having your own source of money keeps you in control of your body, how it allows you to care for your children, pay for your own food, and remain standing if your husband leaves you." The girls were very receptive to this, and as we continued our conversation, I realized why. I told them about my family and how my father came to the U.S. with only one suitcase and the desire to gain an education and create a better life. And then I asked them about their family. This question is such a frivolous one in the U.S., but here in Lesotho, asking someone about their family can be equivalent to asking someone about what has caused the sadness in their life. One girl began, "In 2005, we were 5 in my family." And similarly, every story began with the family being whole 1 year and then losing a member to sickness or the South African mines. Of the 15 girls, only 2 had fathers actively in their lives, only 5 still live with their mothers, the others losing theirs to sickness, most likely HIV. While the stories might seem too sad, there was something hopeful in them. It was the ambitions they still had, the family members they so proudly spoke of, and the honesty with which they shared their life history. It immediately revealed the strength they had that I do not. 2 girls in our group began to cry and could not reveal how their family went from being 5 to 4. I felt sick realizing how much sadness my question caused. But as I stayed, one of the girls told me she would like to talk about her family. I think more and more now I will come home from this trip learning more from my students than I have taught them. Neha is now a PhD student in the bioengineering program at Penn, and she's decided to pursue a PhD project that has an impact in global health. And because of the tremendous impact that we've seen from this program on our students, we began to think about how we could reach out to secondary school students, both in the US and in abroad. So we've developed a course in bioengineering and world health for high school students. It's been approved by the Texas Education Association. We've trained a number of teachers who've taught nearly 2,000 high school students in Houston, most of them minority students. And more recently, we've developed a teacher training program for teachers in Malawi and brought one of the teachers from Houston to help do the professional development course for 18 teachers in Malawi. And we're now running a design competition for high school students for them to be engaged in designing technologies that can have an impact on global health. And this is the winning team from last year, and I love that they incorporated a hula hoop, which they bought for 99 cents at the dollar store, in the design of their low-cost incubator. So I just want to close with what I see as one of the biggest challenges, and that is the challenge of implementation. How do we get prototypes out of the lab and get them into the field and do them in a way that can be sustained over time? Because if we fail to do that, then I think we fail. And it's a very big challenge. I think micro-entrepreneurship may play an important part in that. This is Ewan, one of the students I was telling you about earlier, together with C. Nisbet. And this is the low-cost incubator that was originally developed in Blantyre. And here they are in Nematete, Malawi, and this is a local furniture maker whose shop was across the street from the hospital. And so they worked with him to incorporate the plans that have been developed for him to manufacture the incubator, which is now being used at St. Gabriel's Hospital. And they also worked with community health workers who are volunteers in this community to provide them with backpacks to help provide better screening in the community. And they'll be working this coming year to help them develop small businesses based around the Pure sachet that's made by Procter & Gamble for water purification. So I think the challenges that we face in universities are to make the whole world visible to our students. We have a responsibility to do that. And for them to leave their research programs understanding that we don't just need technology, we need the right technology that really meets the constraints that exist. And I think if we do this, these cost-effective strategies will have global benefit. I need to acknowledge my many partners at Rice, at Baylor, support from Howard Hughes Medical Institute, collaborators at MD Anderson, Mount Sinai Hospital, and Rice, funding from NIBIB and NCI. And I'd like to leave you with one final thought, and that is, as educators and mentors, we help our students start their professional journey. I think we should encourage them to look at the whole world as a destination and to think about who they want to travel with. Let's open their eyes to some of the global challenges. Thank you. I'd be happy to take any questions.
This is more out of curiosity. I mean, it's wonderful and inspiring to see that you have elected to spend your intellect and your energy in devising in fabricating low-cost devices for the global health. And your focus has been mostly on the developing countries' use of these devices. I'm wondering here, why are you not also suggesting that these devices be used right here at home? We are not doing that great in a healthcare system. And in addition to the general use, I don't know how to put delicately, we have neighborhoods where these devices could be quite useful.
I think the dual use aspect is critically important. And so I think many of these technologies have a role both in developed and in developing countries and in improving access to care and hopefully helping to control cost of care.
So may I assume that there are no downsides to these low-cost devices?
Well, I mean, I think it's important to evaluate what is their performance relative to a standard of care. And for the point-of-care diagnostics, I think that means looking at the specificity and sensitivity in a relevant population. And so, particularly for cancer screening, as we look at low prevalence populations, that's crucial, and I think that's what drives cost in the end. So,
thank you.
How do you do quality assurance before you ship it out those equipment? I know the university comes up with a big model.
So the question is, how do you do quality assurance before you ship out these devices? So we it depends on the technology, but for the diagnostic backpacks, for example, everything that's in the diagnostic backpack is commercially available for use in healthcare in the US. What we put together that's special is the packaging and the control electronics. And so we test the control electronics, and then our next step is to evaluate the robustness of that with a partner in the field. And what we have found is that initially the wiring that we were using was not robust enough, and that sometimes we would have problems with the battery reliably delivering power and reliably taking charge. And so we've then responded to that feedback by altering the design. So we go through iterative cycles of design, but it's always very much in close collaboration with a clinical partner.
Thank you. As a Rice alumnus, I'm jealous that this program wasn't available when I was an undergraduate. I'm wondering how a lot of the in the backpack and a lot of the things that you just demonstrated involve contact with humans, and you didn't talk about how you sterilize between patients. I know a lot of times here we have applicators you can throw away, but that probably isn't practical in the field.
For this device, what we do is we use Cydex. And so you can disinfect with Cydex in about 20 minutes. And what we do is we have two of the fiber bundles. So one is in Cydex, the other is being used, and then you change them out, and you just have to screw it in to change them out. So generally speaking, we've tried to use standard disinfection procedures. And
that's in the backpack?
In the backpack, I'm trying to think, for the otoscope and the ophthalmoscope, they do use Cydex for disinfection, for the caps.
I just was wondering if you could touch a little bit more on the sustainability aspects. I know, like, things with the backpacks, that's all stuff from the U.S., and I guess I wanted to know if you were working with other partners besides just, like, just with the local health clinic, but other partners you might be working with to ensure that these things are sustainable, not just over a year or 2 years, but 20 years, 30 years down the road.
So, I mean, I think that is a critical question, and that's the question that keeps me up at night, is how are we going to do that? Because with the backpacks now, as an educational institution, we've made about 30, and I can tell you that I feel I have milked all of the educational value right out of that project, and it's really time for it to leave us and go out into the world. And so the question is, how will that happen in a sustainable way? And there are two possibilities. So one thing we've done is to partner with a faculty member in our business school who now teaches a class called Commercializing Technologies for the Developing World. And so we have a team of MBA students that developed a business plan based around the backpack, assessed the market, and looked at both the NGO and the Ministry of Health marketplace for that. And then we're also thinking about, could we partner with, so that would be the small company route. We're also looking at, can we partner with large companies? So Procter & Gamble, for example, has established a nonprofit component to manufacture and distribute Pure. It's a corporate social responsibility activity. And so we're talking with a variety of different larger companies about whether there might be opportunities for technology like that. So I don't have the answer to what I feel is one of the most important questions, but for us in the next year, a big piece of our effort is going to figuring out that pathway for some of these.
I just had one more comment with that. I think that in order for it to be sustainable also in another country, it has to be almost self-led by businesses in that country, because even if it keeps coming there, if they don't have ownership of it, like you were saying, it's never gonna last.
I agree completely. And for this MBA class, actually, they focused on Rwanda, and the students went to Rwanda as part of the course and worked with the Rwandan Development Board and local entrepreneurs, because I think if you don't have partnership, then you don't get sustainable dissemination.
To touch at sort of a different angle of the sustainability question, I'm wondering what sort of tactics you have for training the people who use, say, the backpacks and various of the other technologies that you've implemented in case something breaks or in case they need to replace something, and how you deal with either malfunctioning equipment or if you run out of a reagent or a particular part.
Right. So we have done a couple of things. With the backpack, we began by doing individual one-on-one training when we were just sending the first ones out into the field. Now we have developed a user manual that's both in English and Spanish, and we have a training video that is also in English and Spanish. And we've done video conference training, so the physicians that went to Myanmar, actually we did a video conference training to ship them the backpack, and they took it there. And they provided us with some really excellent feedback about some things that broke when they were there that made us realize that we needed to change some of the electrical connections. So we're trying to develop job aids and user manuals for these technologies about the time they get to the second or third prototype.
Thank you.
I have a couple of sociology questions. The first one is, I've been told that frequently in a country which is poorer than the United States, if you try to bring a technology there that's tailored to their use and doesn't have the sophistication, and somebody else asked this question, of the American medical estate, it's frequently not looked upon as something favorable. The other question is, how do you turn this sort of low-tech technology into a academically viable enterprise? Cheap technology and things which are basically adaptation of simple techniques don't often get the approbation that perhaps they deserve.
Yeah, so, well, in answer to the first question, I haven't found the receptiveness to be an issue. The partners that we have worked with want things that will help them do their job better and care for their patients better. And so if we can provide something that will help them do that, they're very receptive, whether it's FDA approved or whether it is an investigational device. They're very receptive to that. I think in answer to the second question, it's difficult. There's no question about that. The way that I got into this was in setting up an undergraduate education program, not because it was initially part of my research lab. And I think for a beginning assistant professor, it would be a very difficult and probably unwise thing to do, as your only source of investigation. But I think if we are able to show benefit both in developed and developing countries, I'm hopeful that that will begin to change. And if we're able to leverage some of the microfabrication in consumer electronics, which actually has a very large amount of engineering. I don't mean to trivialize it because there's a lot of technology development that's required for that. That I think is academically viable and useful.
Hi, thank you for your talk. I just wanted to ask you a sort of practical question. So for me, for example, who's a postdoc here, I do basic science research. What do you, in terms of how to get plugged in or how to do basic science research and get connected to people who are thinking a little bit more specifically about the problems, how we could collaborate. What kind of ideas or suggestions do you have?
I would have two suggestions. One is I would think about taking a course through a school of public health in international health, because it's a great way to learn just what are the issues. And then what was most valuable for me was to find collaborators who are already engaged in doing this. And I learned so much from them, and they were so generous in sharing their contacts and their knowledge. That was absolutely critical. And usually people who are doing that, they really care about it and they want to convert other people to join them. And so they're usually very, very willing to share that.